Hey guys, hope everything's going all right. I wanted to get you a video on how to do section 9.2 geometric sequences. So geometric sequences, a lot of it works the same way as arithmetic sequences. The difference is we're dealing with a different type of pattern. With arithmetic sequences, if you remember, we were dealing with addition, to get from one term to the next. But here we're using multiplication. Okay, so we're instead of adding, we're just simply multiplying by 2, multiplying by 2. Okay, well, when you multiply, things act a little bit different, so we need some different formulas. So in this case, we're actually going to have a different term as well. So here, because we're multiplying by 2 over and over and over, that's not a common difference. That's actually what we call a common ratio. Okay, because basically you can take any term, we'll say a sub 4, divide it by the term before it. So if I take 24 and I divide it by 12, or I take 12 and divide it by 6, or 6 divided by 3, I can take any term and divide it by the term before it. So if I just subtract 1 from that, okay, I will get the same number over and over and over again. We call that R. Okay, so we're not dealing with D's, that's the common difference. Now we're dealing with a common ratio. Okay, now again, we're going to have two different ways to talk about these. We're going to have a recursive way and we're going to have an explicit way. Again, the recursive way, it's kind of the long way of doing things. Yeah, if I wanted to find the 24th term of the sequence, absolutely, I could just multiply by 2 over and over and over and over again. And I could, if I want to find a sub 1, or I know a sub 1 is 3, and I could just multiply by 2 to get 6, and multiply by 2 again to get 12, and keep this pattern going, okay? And that basically becomes my recursive definition, where I can take any term, or I can find any term by taking the term before it, or multiplying the term before it by R, okay? Which is basically just this formula up here rearranged, okay? If I just multiply both sides by that a sub n minus 1, I get that formula down there, okay? Again, the recursive way, it works if I was trying to find the 5th or the 6th or the 7th term, but if I was trying to find the 82nd term, that's going to take me all day long. So we want to have an explicit way of doing this, okay? And again, we can think of it in the same idea where a sub 1 we know is 3, and we got a sub 2 by doing 3 times 2. And we got a sub 3 by doing 3 times 2 times 2. And we got a sub 4 by doing the same thing. Well, basically, you could think of this as 3 times 2 squared. And this would be, we're multiplying by 2 3 times, and so on, and so on, and so on. So the 5th term, we would multiply by 2 to the 4th power, and so on and so on. Well, this idea gives us our explicit formula, where we can find any term by taking my first term, okay, and multiplying it by my R value, not to the same n power, but to the n minus 1 power. So this is going to be our main explicit formula that we're going to use over and over and over again. And that's the formula that's going to give us, if I wanted to find the 82nd term of this pattern, all I would have to do to find a sub 82 would be find my a sub 1, which I know is 3. I know my R value is 2, and then I would just raise it to the 81st power. I could type that in the calculator and get an answer. Of course, that one would be pretty darn big. All right. And just as a side note, geometric patterns can go down. They don't have to go up. We can have exponential decay, so to speak. And a lot of people would think I'm dividing by 2 divided by 2, but if I follow the definition of my common ratio, where I take any term, divide it by the term before it, I just get 1/2. So it's just like exponential decay. If my R value is less than 1 or between 0 and 1, then the pattern would go down. Also, this geometric sequences, I can have some pretty interesting patterns. When you think of something like if I had an a sub 1 of, let's say, 5, for example, and then I take an R value and I have a -2. Well, then that means the pattern is going to go 5. 5 times -2 would be -10, times -2 would be +20, and then -40, +80. So it can go positive, negative, positive, negative, positive, negative, if the R value is negative. And this is actually going to create some problems for us along the way, and I'll show you that in a second. Okay, so let's use the formula and try some examples. So this one says I have to find a sub 8 if they gave us the fourth term and the R value. Well, in this case, I could do it either way. I could do it recursively, where I already know the fourth term. I could just multiply, and get to the eighth term fairly quickly. That wouldn't take me that long. If I know the fourth term is 16, then I also know the fifth term must be 8. I know the sixth term would be 4. The seventh term would be 2. And then that means I know the eighth term would be 1. Okay? So I know the answer is 1. But just because this problem could arise and then maybe it said 81 instead of 8. Okay? So I want to have an explicit way of doing this as well, not just a recursive way. What I could do is I could use the explicit formula. The a sub n equals a sub 1 times r to the n minus 1. Could use that formula. That means this a sub 4 equals 16 means there must have been an equation that equaled 16. So I could put 16 here. Now at this point in time, the n value is going to be 4. Now I don't know my a sub 1. I do know my R value, and then I know my n minus 1 would be 3. Okay, so 1/2 times 1/2 times 1/2 would be 1/8 times a sub 1 is equal to 16. I could multiply by the reciprocal. I'm going to cheat here because, 16, 32, 64. It should be 128, I'm pretty sure, but just to double check, 16 times 8. Yep, I was right. Go away. Okay, so 128. So now that I know my a sub 1 is 128, now I can use my explicit formula again to find a sub 8 would equal my a sub 1, which I just found is 128, times my r, which I knew all along, to the n minus 1, which was 7, and I could calculate that out. 1/2 to the 7th power. I could type in 0.5 raised to the 7th power. I could get that as a decimal, or if I wanted as a fraction, that would be 1/28 times 128, and I end up with 128 times 1 over 128, which is obviously, we get the same answer. Okay, so this might be a little bit better way of doing that, only because, in this particular problem, this might have been a faster way of doing it, but we want to have that explicit way just in case the numbers are a little farther apart. Okay, let's try one like we did yesterday with where they gave us 2 random terms. Now we do have to be very careful with these, and I'll show you why. We can do them the same way. I told you before, if they give us 2 random terms, you should be thinking system of equations all along. Now, I do recommend doing the bigger term first, and I'll show you why in a second. So write an equation for this 216. There must have been an equation that equaled 216. So what was that? 216 would have had to equal my a sub 1, which I don't know, times my r, which I don't know. But in this case, I do know my n minus 1 because at this point in time, my n value was 8. So my n minus 1 is 7. Now, there must have been a different equation that equaled 54, okay? Again, don't know my a sub 1 yet, don't know my r, but at this point in time, my n value was 6, so my n minus 1 would be 5. Now, this is a little bit different of a system of equations because I'm dealing with exponents here. I can't actually subtract these two because that would be the same thing as doing like 4x to the 7th minus 4x to the 5th. I can't subtract these. They're not like terms. But what I can do here is I could divide, okay? Now, when I divide these, my a sub 1s cancel as well, okay? So my a sub 1s would cancel. My division rule with exponents tells me to subtract those. So I end up with r to the second. And then all I have to do is figure out what 216 divided by 54 is. And I get 4. Okay. Now, the next step here is very crucial because how do you get rid of that squared? Well, we take a square root. Well, that's important because the answer to any even root is a positive or a negative 2. There's actually going to be two different answers to this problem, okay? One with an r value of 2, one with an r value of negative 2. Because there could be two different patterns. One where everything just stays positive. We times by 2, we times by 2, we times by 2. The other one could be, in this case, negative, where we alternate. Remember, the negative exponent just means we're alternating positive, negative, positive, negative, positive, negative. It could go positive, a sub 7 would be negative, a sub 8 would be positive. So there actually is going to be two different answers to this. Each of these will have their own, get rid of this for a second, you don't need that, a sub 1, okay? So we got to find those individual. Well, you solve any system the same way before. You just plug them back in. And I would plug them into the second one. So 54 equals a sub 1 times 2 to the 5th power. So basically we have to do 54 divided by 2 to the 5th. All right, so 54 divided by 2 raised to the 5th power. And I get 1.68. I'll put that as a fraction just to make it a little bit nicer of a nicer number, which is 27 over 16. So this is one answer to that question. Okay. Now, there is a different answer because in this case, when I plug in a negative 2 here, well, when I raise it to the 5th power, that's going to be a negative. So then I do a positive divided by negative, and I will get the same number. It's just going to be negative in this case. But you can imagine with slight variations of the same question, am I always going to have two solutions here? No, the only reason I ended up with two solutions here is because this number happened to be an even number, okay? If it was a 4, same thing. But when I subtract, if I got a 3, a third root does not have two solutions, so I'm not always going to have multiple solutions here. Also, I could have the same a sub 1 once in a while, even with two different solutions, because it all depends on the alternation of positive, negative, positive, negative. If this was an 8 and a 6, I'd still subtract the 2. I'd still have two solutions. But when I plug in the negative into, if this was an even number, then, it would be a positive still, so I would still have both positive. So you do have to be a little bit careful there on some varying questions. And an example, that you might run into, I didn't put one on here. Here. So here's another one, basically the same type of question. But now I have, again, two problems. I like to put the bigger term first. So 2 had to be an equation, or there had to be an equation that equaled 2. It would equal a sub 1 times r to the 7th, because n minus 1. When I do this one, the 16 would have had to equal a sub 1 times r to the 4th. Again, I'm going to divide, same process as before. When I divide, I subtract my exponents, r to the 3rd, the a sub 1's canceled. 2 divided by 16 is 1/8, okay? Now, because I'm left with a odd number here, when I take the third root of 1/8, I'm not going to have multiple solutions. So the third root of 8 is 2, so my r value is just 1/2. I'm not going to have multiple solutions here. Okay? So all I have to do, since I know my r value is 1/2, I got to figure out my a sub 1 that goes along with it. And again, I just plug it into one of these two equations. It really doesn't matter. 16 would have had to equal a sub 1 times, now it's 1/2 to the 4th. 1/2 to the 4th. 2 times 2 is 4, times 2 is 8, times 2 is 16, so it's 1/16. A sub 1 equals 16. And then I just got to figure out what 16 squared is. I believe 16 times 16. I believe it's 256. I'm correct. So there is my a sub 1. Okay. So with these, you do just have to be conscious of, if at all, if you ever do take an even root anywhere in a problem, you're going to end up with multiple solutions because of that plus or minus. Just remember, the r's could be positive or they could be negative at any point in time. Okay? All right, so another problem similar to what we did yesterday. Let's insert 4 geometric means between 1/3 and 81. So what that means is we have 1/3, 1, 2, 3, 4, and then 81. Okay, so we're going to do this very similar to the way we did the arithmetic ones. We make this a sub 1, that means that's a sub 2, a sub 3, a sub 4, a sub 5, that means that's a sub 6. Okay, and again, we write an equation for that last one. So 81 must have equaled an equation. Well, that equation would be my a sub 1, which I know, times my r value to the n minus 1, which in this case, again, would be 5. And now we can just solve this. How do you get rid of that 1/3? We times by 3. Well, 81 times 3 243. Okay. And then, how do you get rid of that 5th power? We take the 5th root. And if you remember, there's an easy way to type that in your calculator. We just raise that answer to the 1/5 power. That's the easy way to take the 5th root, and we get 3. Now, again, because this was an odd number, okay, because that 5 is an odd number, I don't have to worry about plus or minus here. If it was an even number, then I would have to worry about it plus or minus, and I could have two different patterns. Now, once you have the r here, the easiest way to finish this is just recursively. So just multiply by 3. So 1/3 times 3 is 1, times 3 is 3, times 3 is 9, times 3 is 27, 27 times 3, sure enough, is 81. Okay? So one very similar to that could end up having two different solutions is this one. Insert 5 geometric means. So I have 32 and I have to insert 1, 2, 3, 4, 5 numbers, and then I have a half. So again, this is my a sub 1, a sub 2, 3, 4, 5, 6. Now I have a sub 7. Again, we write an equation for that one. So that means 1/2 would have had to equal my a sub 1 times my r to the n minus 1. So now I have an even exponent, which means I'm going to have two different patterns here. When I divide by 32 or multiply by the reciprocal, I end up with 1/64th. And then I have to take the 6th root of 1/64th. Well, 64 raised to the 1/6 power is going to be 2. So what that means is when I take the 6th root of 1/64, I'm going to get plus and minus 1/2. So there's two different patterns here. One with r is equal to 2, or 1/2, I'm sorry. One where r is equal to negative 1/2. Now, if r is equal to 1/2, the pattern goes 32, 16, 8, 4, 2, 1, 1/2. And that's one way to get from a 32 to 1/2. But if r is negative 1/2, there's going to be a different pattern because it'll go positive, but then it would be negative 16, positive 8, negative 4, positive 2, negative 1, positive 1/2. So there's two different patterns of how to get from a 32 to a 1/2. You could stay positive the whole way, or you could alternate. Now, if you remember, going back to the one we just did before, the reason this one wouldn't work is because if you alternated positive, this would be negative, positive, negative, positive, that would have had to be a negative. So sometimes it works, sometimes it doesn't, okay? So that's the majority of it. Now, there is something different when you start talking about geometric patterns, and that's what we call a mean proportional. Basically, it's very similar to the geometric means where we're inserting a number between, but that's the key word here, is the answer has to be between, okay? Now, you could do it the long way, the same way we just did the other ones, where basically the idea here is we have a negative 12. We want to insert one mean proportional in between those. You could do it, oops, that's a 108. The same way, that's a sub 1, it's a sub 3. You could do it the same way. But keep in mind, the answer has to be between. That's going to be important in a second. You could do it this way, or there's a simple way. All you have to do is multiply the two numbers together and take the square root. And that's it. But keep that between word in mind, because there is going to be two solutions here. So if I do that negative 12 and the 108, well, if I multiply a negative 12 times a negative 108, I'm going to get a positive. So then I can take the square root. Well, anytime I take the square root, there's two solutions. There's a positive solution and there's a negative solution. Since the answer has to be between, the only answer that is between these two negative numbers would be negative 36. And there's your mean proportional. Same way you could do this one over here. You could just multiply the 15 and the 60. So 15 times 60. Take the square root of that. So you're going to get 30. And then the answer, because it's plus or minus, it could be positive or it could be negative, but because the answer has to be between, then the answer has to be 30. Okay? And it should follow a pattern of how to get from one term to the next. In this case, if you take 15 times it by 2, you get 30, times it by 2, you get 60. So again, it's going to follow some sort of pattern. This one over here, timesing by 3. But with mean proportional, another way to think of this is the R has to be a positive number. Okay, so that way you're not, the answer ends up being between. Okay, but basically just to summarize, so with arithmetic sequences, we had two formulas. We had our D formula, or our recursive formula. That means I can find any term by taking the term before it and adding my D value. And then my formula ended up A sub n equaled my A sub 1 plus my D n number of times. So those are my two formulas for arithmetic. So now my two formulas for geometric are similar. I can find any term by taking the term before it and now multiplying by R, or I can find any term by finding my first term and multiplying it by R raised to the n minus 1 power. Okay? And again, arithmetic sequences have to be, you're adding, addition from one term to the next, and geometric sequences has to be multiplication. Okay? That's all I got. Try some problems out of the book or out of the worksheets and or on Khan Academy, and let me know if you have any questions. You guys have a good one.